Information channel. The information channel, we have two sources, input source and output source of messages, and between them we have a channel. These messages are transmitted through noisy channel. Such channel, discrete memoryless channel DMC, is defined by a probabilistic model, transition probabilities, conditional probabilities that can be expressed graphically. Between every pair we have one probability, total of n, product of mn transition probabilities. They describe such noisy channel. Such channel can be expressed graphically by this drawing. This is input source, output source, and noisy channel. Noisy means we have a leak in a pipeline, information loss. We have a contamination pumped to this pipeline, the misinformation. So the mutual information is input information minus information loss, or output information minus misinformation. If this circle is information, input information, and this is what we see at the output information, and this, obviously, these two circles overlap, and only what is really interesting, what matters, is this common part. It is a mutual information about occurrence of message from source X as seen from the output. Unit is obviously 1 bit, not 1. It's bit. This is binary source, characterized by two probabilities, transition probabilities. Probabilistic model of the source X is given. Then, straightforward, from these probabilities we may calculate the misinformation. Then, in step 2, we may calculate the output probabilities from this formula. And having output probabilities, we may calculate entropy of the output source, and mutual information is information of the output source minus misinformation already calculated. Now, this mutual information is normally expressed as a normalized mutual information, referred to the maximum information produced by source X. And for this data, this normalized mutual information is only 9%, which is very low. This is information channel, and we may model a measurement as a transmission of data through a noisy information channel. This is measured quantity, this is measuring device, and then it is a measurement result as the output source. For example, the measured quantity, it can be physical quantity, temperature, pressure, etc. It can be non-physical, the student's knowledge. The exam can be modeled by noisy information channel, and we may calculate the mutual information. It is information about student's knowledge based on the exam results. These data are real data. The examination took place 2 years ago. I have divided all students into two parts. The first part is students that solve many questions, the quiz questions, more than 50%, and the other part are students that solved less than 50% of quiz questions. And these are results, exam results, pass and fail. So I have assumed that my input and output are binary. These are real data. By coincidence, this channel is a symmetric one, and it is easy to calculate that the mutual information of this channel is 0.41. 0.41, well, if we take the normalized mutual information, it is around 41%. Is it much? Oh, satisfactory. Actually, what is really quite high is the percentage 14% of students, students that have solved not too many questions, and they have passed. Now, why? Because the threshold, examination threshold, was only 35%. 3.5 points out of 10 was enough to pass, and because of that, number of students that have passed, however they didn't spend too much time on solving quizzes, was 14%, and this mutual information is only 0.41. This concept of information channel can be also used to test a measurement program development. If we have a circuit system under test that has m states, and we have some number of tests available, and the question is which test is the best. The test that gives the maximum mutual information is the best. The next screencast is binary channel and other special cases.